Do you believe in star signs? Do you believe that there are hidden rules that control our lives? For thousands of years, people believed that there were secrets in nature of great importance, and that those who knew those secrets would wield special power. By the middle of the 19th century, scientists were on the verge of discovering the universe's most important secret. They were about to discover that there was something more real than anything that we can see and touch, that flits like a ghost behind everything that happens and keeps control of it all. The 19th century was the age of steam. Fires raged under huge boilers which produced steam for trains, factories and ships. Electricity had been discovered. The race was on to design better, bigger and more cost-effective machines. To do this, scientists had realised the importance of accurate measurements, and they'd invented a number of instruments, such as the thermometer for measuring heat, the barometer for measuring pressure, the chronometer for accurate timing, and the beam balance for measuring weight. So they began to investigate the forces that make machines go. Nicolas Carnot wrote an important book called Reflections on the Motive Power of Fire. Like many, he believed that heat was a special substance called caloric, which the fire let out of the fuel. When the caloric went into the water, it let out steam. Carnot pointed out that the amount of caloric was measurable, and you could track where it went. Caloric, he said, was dissipated, but it was never lost. The trouble with caloric, however, was that although it explained how heat could do work, it couldn't explain how work could produce heat. There were plenty of examples in the factories of how the friction of drilling or rubbing made things hot. But how could rubbing things together produce a new substance? A better theory was that heat was really vibration of the atoms of which everything is composed. Lots of vibration, lots of heat. And it was easy to see how friction could cause atoms to vibrate. James Joule set out to find the secrets of heat by experimenting and measuring. He spent 35 years of his life measuring the heat of electric currents, forcing water through tubes to see how it heated them, compressing air, rubbing things to see how much work produced how much heat. Joule measured the interaction with heat of everything he could think of. In this experiment, the paddle wheels were designed to stir the water, which had its temperature carefully measured. Weights turned the wheel, and Joule noted how much the temperature increased compared to the movement of the weights. The more carefully he measured and recorded, the more clearly emerged a great secret. Any kind of pressure, motion, light, gravity, electricity, any kind of work at all, as Joule put it, any kind of living force or attraction was convertible to heat and could be converted from heat. In short, he said, they are all convertible to one another. And then the punchline. In these conversions, nothing is lost. So Carnot was right. Nothing is lost. nature maintains a great constant of something that can always be expressed as heat. But of course, it isn't always heat. It could be the work of an engine. It could be the pull of gravity or the effort of muscles. It could be the wind or the sunlight. But the work it could do could always be converted to heat and therefore measured in terms of heat. Heat was like a money value that could be put on any kind of action. And nature kept a strict accounting system. Whatever this strange power of action was, there was just so much of it in the universe. You could move it around, but you could not get it from nothing or make it disappear. It's the most important law in science, and everything in the universe that we know obeys it. Not knowing why this should be so, scientists did what they've often had to do. They gave the mystery a name and got on with measuring and using it. They called it energy, from the Greek meaning containing work. Today, we have hardly any better understanding of what energy is, or why energy is so, than our great-grandfathers who discovered its all-powerful law. We know energy simply as the ability to do work. To honour Joule's lifelong commitment, we measure it in joules. And almost in celebration, we've found more ways to convert and use energy than any other civilization before us. We have found new forms of energy that Joule never dreamed of, such as nuclear energy. We have converted vast amounts of fossil fuels to heat, and thereby to mechanical energy and electrical energy. And with our air conditioners and our heaters, we've converted it back to heat again. Energy, or as it is sometimes called, the capacity to do work, may be stored and delivered in truly amazing ways. For example, the LPG gas in this hot air balloon's fuel tanks releases heat when it burns, blasting hot air into the balloon. The air inside the balloon now has more energy compared to the cool air outside. And one way that this energy difference expresses itself is in giving the balloon an upwards push. The balloon gains both upward kinetic energy of movement and stored gravitational energy as it rises up higher and higher. But the energy transfer is inefficient. Heat is constantly leaking away, and it needs to be replaced. Here's another example of the complicated exchanges of energy that go on all the time. The trampolinist uses her muscles to create thrust, but gravity removes the kinetic energy of her bounce until she stops and falls. Gravity then releases the energy it has magically absorbed into downwards kinetic energy. And this is caught, in turn, by the elastic trampoline, which, like gravity, absorbs the kinetic energy of the fall and then releases it again into a new upward thrust. Once again, however, these energy exchanges are imperfect, leaking partly into heat. So muscles, trampoline, and the surrounding air are warmed up. There's absolutely no problem with using energy, except that we are tending to run out of fossil fuels and polluting the place in the process. For a while, nuclear energy looked good because the supplies are extensive. But nuclear waste is even worse than smoke, haze, carbon dioxide and acid rain. As populations increase and energy demands skyrocket into a new century, what we need are non-polluting, renewable forms of energy. The kinds, in fact, on which the planet has run for millions of years before humankind. Two forms of renewable energy of which Australia has plenty are wind and sunshine. Unfortunately, both these forms of energy are low intensity. To get industrial power from the wind requires large wind farms, and to get similar amounts from the sun means large arrays of solar collectors. Of course, the wind doesn't always blow, and the sun doesn't shine at night, so we also need ways to store the energy gained for times when it isn't directly available. Plus, we need to find ways of producing more cost-efficient collection devices. We need to do the same for solar power as our forefathers did with steam power. One place where they're hard at work improving solar panels is the University of New South Wales. They also build solar cars and race them.
Every 3 years, Australia hosts the World Solar Challenge, a car race from Darwin to Adelaide. What's special about the cars in this race, cars such as SunSwift, is that they're solar cars. That is, cars that run only on sunlight.
The Solar Challenge is regarded as more than a sport. Each car is a test bed for the engineering of the future because the race rules encourage the most efficient use of the energy of the sun.
The rules limit the area of sunshine that you can collect, so to make a solar car go really fast, you have to use energy very efficiently. That is, whenever you convert energy from one form to another, you have to do so without wasting too much. First, you need efficient solar cells, such as the solar cells we make here at the University of New South Wales, the best in the world. You then need to convert that energy into mechanical energy to make the car move, which is done using a highly efficient electric motor. We also need to store some of the energy for cloudy days, which means using an efficient rechargeable battery. It's the energy that finally gets to the wheels that makes the car move. But once it's moving, wind and rolling resistance are constantly trying to slow the car down. So we need to streamline the car and make it very light. Only by being so efficient with energy do you have a chance of winning the race. A solar car is really a symbol of today's energy questions. How can we harness energy from sources with little environmental impact, and how can we use that energy as efficiently as possible? The World Solar Challenge and even model solar car races show that we're getting better at answering these questions because the cars are going faster and faster, even though the brakes might fail or other things sometimes go wrong.
In a larger sense, the finishing line is not the end of this race. It's just the beginning of preparation for the next World Solar Challenge, and more importantly, it's part of a new attitude towards energy.
Videotapes from this series are available by contacting ABC television program sales in your capital city.